Good afternoon. We are East Tennessee State University. Our team is the Bucs stop here, and this is our solution to the 2021 Solar District Cup City of Denver and Auraria Higher Education Center use case. First and foremost, we would like to thank the organizers of this competition as well as the judges. We are pleased to present these recommendations and proposals to the investors and end customers. Next slide, please. This is the 5th year of our BSc in General Engineering program. We are the second graduating class from this major, and the team members are the following along with their contributions to the use case. And this project also serves as our group's capstone project. Bailey Couch, construction plan and timeline. Wes Dotson, building and site plans and assistance to the resiliency solution. Dawson Kowalski, system layout and design, Aurora Solar. Myself, Carter Manus, resiliency and battery analysis and alternative solutions and document gatekeeping. William Schaff, distribution impact analysis, OpenDSS and LP optimization. Mason Smith, financial analysis and models. And Dr. Daniel Connors, our ETSU professor and faculty advisor. Next slide, please. For the Auraria campus, 3.12 megawatt system size with batteries in each building for a total of a 34-week construction timeline. These batteries allow for more solar to be built out and covered for the nighttime usage. The total project sale price is $8.2 million with a PPA of a little over 11 cents per kilowatt hour and an IRR of 7.5%. The photovoltaic systems produces 4.39 million kilowatt hours in the first year, offsetting 55% of the campus's load and reducing carbon emissions by roughly 88,000 tons of CO2 in 30 years. The resiliency solution for the science building involved using a 1.02 megawatt hour backup generator costing $316,000, saving $83,800 versus a $400,000 battery solution to cover 100% resiliency against a 4-hour outage. For the Denver Community Solar Garden, a 5 megawatt total system size for a total of a 33-week construction timeline with a total project sales price of $9.3 million, a PPA of right over 6 cents per kilowatt hour, and an IRR of 4.3%, with the city of Denver itself earning $105,000 over 20 years. Now you'll hear more about our design.
Okay. The team used mathematical programming to optimize the design. Linear programming models were developed using the design constraints, which were then solved to obtain system design parameters. The models calculate photovoltaic energy as a function of the system size, irradiance, and efficiency. The models consider constraints such as rooftop size, export limits, thermal and voltage regulations, as well as the community solar garden legal size limitations. The linear program contains objective functions that can maximize PVE production or minimize the battery sizes in the system. The system power flow was modeled based on Kirchhoff circuit laws. In each time interval, the building load is satisfied by either PVE production or energy purchased from the utility company. Any excess PVE may then either be stored by a battery or exported to satisfy another building's load within the campus. An efficiency parameter was incorporated in the battery model to capture the losses in energy experienced by physical batteries. Once all of the building's loads have been satisfied, the excess PVE is exported to the substation. However, this exporting is limited by the distribution's exporting constraints. The optimization model was based on this balance of power flow.
So for the Auraria campus, we were given loads for 8 of the buildings on the campus, and we developed our PV systems on all of these 8 buildings using the Aurora Solar software and used batteries on all of these buildings that equates to half a day of storage that allows us to cover some of the nighttime energy needs and produce the 4.4 million kilowatt hours annually. For the Denver Community Solar Garden, we developed a maximum size of 5 megawatts using the Solar Aurora software based on the Community Solar Modernization Act. The system was designed on the Denver Convention Center and the Denver Performing Arts Complex and produces 7.3 million kilowatt hours annually. Next slide. So for the equipment, we was used across all designs to ensure swift procurement for installation. The inverters were chosen based on their production capabilities, the ability of the required DC optimizer to mitigate any losses from the panels, allowing for more production from each panel. Panels on the Aurora campus were all oriented southeast on the campus to maximize solar per panel and to match the existing system on the Aurora library. The panels on the Denver CSG were oriented facing south, which is the same as the existing system on the Denver Convention Center. All the equipment was also chosen because they provide better performance and have longer warranties over their expected life of the system. Next slide.
The team modeled PV systems in OpenDSS to analyze the design's impact on the distribution system. According to our analysis without batteries, the maximum feasible PV systems do not produce any voltage violations in the distribution system. However, the simulation detected 4 transformers with significant overloading. In the team's final design, constraints were modeled in the linear program to limit the transformer overloading as to not exceed 110% of the KVA rating. The LP solution indicated that a large battery in each building would be necessary to maximize the PVE production. This battery in the science building is separate from the resiliency solution.
So if you look in the top left corner, you can see our investor financial information figure. The first 2 rows of this are selected solutions, one for Auraria, one for Denver. The other 2 show the other solutions we went through in the process of trying to find the optimum for customers, for investors. And looking again at this figure, you can see our Auraria sale price of $8.2 million and that the hurdle rate of 7.5% is obtained for the investors. The customers on this side would stand to have a PPA of 11.88 cents per kilowatt hour. If you look at the bottom of our green figure here, you can see our solution's environmental impact and that our proposal comes with the benefit of 80.5 thousand tons less CO2 emitted over the panel's lifespan, or 55%. Moving on to the top right figure here, you can see that the Auraria customers would stand to have a NPV increase or power bill increase at 20 years of $2.5 million. Now, if the campus is serious about going green, then we believe this is their best solution. Looking back at our top table there, you can see Denver is a flip on this story. Due to the required credit and discount rates, even when our system was sized up to 5 megawatts from the initial 2, 7.5% is not possible. 4.4 is the best that we could obtain for the investors and still maintain a meaningful credit rate for the customers. The bottom right figure shows that the city of Denver, though, would boast savings of $105,000 at 20 years, and our residential and commercial customers stand to save $29,000 and $6,000 respectively. The 55% emission reductions from our initial calculations stand to apply here as well, but without more usage information, we couldn't nail down an exact tonnage for that. Next slide.
The development plan consisted of both the building site plan and the construction plan. For the building site plan, we needed to look at building codes, master plans, and zoning requirements. We followed the master plans on the Auraria side. The master plans consisted of renovating the buildings and not adding any PV systems. Both sides already had existing PV systems that we had to avoid. We decided to put all of our panels on roofs. The Denver side is putting a roof loft in that we also had to avoid. We found these zoning areas for each of the district case and found there were no specific requirements for PV systems we had to follow. In the lower left section of this slide, you can see a map that represents all zoning areas. The solution does help the campus reach their sustainability goals since we're cutting the amount of energy they need to buy by 40%. For the construction plan, we needed to identify all applicable construction permits, create a construction timeline, and identify risk to project success. Denver Development Services give a list of all applicable building, fire, and electric codes that must be followed to acquire the necessary permits. All permits must be acquired before construction can begin. After all the preliminary steps have been completed, the contractor or construction company can apply for the permits required by the municipality. Construction timelines were estimated by looking at the size of the photovoltaic system being built. Time estimates were given by Select Energy, a solar energy company. They give timeline estimates for permit procurement and all construction based on the system size. In the lower right section of this slide, you can see an example timeline. Our construction staging plan will contain an existing site plan, truck and crane staging, material storage, construction hours, construction fencing, and construction dumpsters. The major risk to the success of the construction plan are time, budget, and community support. Next slide.
The resiliency analysis was conducted using a MATLAB script that took the science building's usage data in 15-minute intervals. The script was ran for a total of 4 hours. That is the national average of a major power outage. This determined that 1 megawatt hour of energy would be required to cover the building entirely for the 4-hour outage. This is based on our plot showing the amount of energy necessary to cover a certain percentage of resiliency for the endured outage. The cost of using batteries for this solution would be a minimum of $400,000 in a 20-year period, as the maximum lifespan for an industrial grade battery of this quality is roughly 10 years due to the colder climate. From this, we researched alternative solutions, and the team settled on the Cummins KTA 50G3 1.02 megawatt diesel backup generator, as it came in at a total cost of $316,200, being $83,800 less than the two batteries. This price includes the generator, all necessary hardware, and ample fuel to cover the 4-hour outage. Next slide, please.
Our extensive modeling revealed issues that with the provided information from the competition organizers. The original load profiles we were given were mislabeled. They were originally labeled as kilowatt hours instead of kilowatts. This led to us having loads 4 times the actual load. The Learning Center building was also not connected to the grid in OpenDSS, and the given Excel spreadsheets for the financial analysis also contained a few errors. The calculation for the net present value was incorrect. In addition, the AC-DC conversion was not used in the spreadsheet calculations. Due to the programming models we created, we were able to seamlessly and quickly update this information the last few days of the competition when these errors were confirmed to be incorrect by the competition organizers. Next slide, please. So in conclusion, on the Auraria side, we maximized the PV production to generate 64% of the campus's energy needs. This allowed a significant reduction in carbon emissions. Investors will get an IRR of 7.5%, and the resiliency solution provides backup capabilities for 4 hours. On the community solar garden side, the structure limits investor IRR potential, and the city of Denver earns $105,000 over 20 years. These solutions were developed based on our engineering background. This allowed us to model and optimize our system design. Our modeling was robust and could be rapidly updated to address changing objectives and system parameters. And now we can take questions.